Hello, welcome back. In this video we'll discuss the losses in optical fibers. As you know, in the case of optical fibers, the signal in the optical fiber will propagate in the form of light. And as light propagates through the fiber, it suffers loss of amplitude and also change in shape of the signal. The loss of amplitude is referred to as attenuation, and the change in the shape of the signal is called as the distortion. So there are essentially two types of losses. The first one is loss of amplitude, and the second one is change in shape of the signal. The loss of amplitude is referred to as attenuation, and the changes in the shape of the signal is referred to as distortion. Consider an optical signal in the form of a pulse like this. Suppose this light pulse is launched into an optical fiber. After propagating down the optical fiber for a distance, say L, suppose the intensity of the pulse drops down to so much. Initially, when the light pulse is launched into the optical fiber, say its intensity is A, and at the output end of the optical fiber, after traveling down L kilometers through the optical fiber, if the intensity of the light becomes A prime, where A prime is less than A, the variations in the intensity are due to the attenuation. Attenuation essentially contributes to the reduction of the signal intensity or strength. Similarly, if you have a light pulse like this, and after traveling through the optical fiber over a distance, say L kilometers, at the end of the fiber, if you receive a signal which is not a rectangular pulse, rather a very smooth curve like that, then you call such a thing as distortion. We shall now discuss about the attenuation. As we have seen earlier, attenuation essentially contributes to the reduction of the strength of the signal or intensity of the light pulse. In optical fibers, the attenuation is defined in this fashion. Attenuation is the ratio of optical output power from a fiber of length L to the input optical power. Essentially, it is a ratio between the output optical power to the input optical power. Suppose you have an optical fiber and you launch power Pi at the input end. Say this is the input end, and at this point we have the output end, and the power measured there is say P0. If the length of the fiber is say L units, generally L will be in kilometers, then we write P0 is the power at the output end and Pi is the power that is launched into the fiber at the input end. Say L is the length of the fiber. One can write the output power in terms of an exponential function. The output power is equal to the input power times some exponential minus alpha L. Say this is 1. Here alpha is a constant which is known as the attenuation coefficient. Since length is taken in kilometers, alpha will be per kilometer if L is expressed in kilometers. We shall take the logarithm on either sides of 1 to write an expression like this. Alpha is equal to 1 over L log Pi over P0. And to obtain alpha in dB per kilometer, we write alpha as dB per kilometer as 10 over L log Pi over P0. Please note that this is a natural logarithm, and here we have logarithm to the base 10. The attenuation in an optical fiber can be expressed in terms of dB per kilometer as 10 over L log Pi upon P0, where Pi is the power at the input end and Po is the power delivered at the output end. If P0 is equal to Pi, which means the optical power measured at the output end is equal to the optical power at the input end or at the launch end. Under such conditions, alpha will be equal to 0, which implies there is no attenuation in the optical fiber, and such an optical fiber does not exist. Different mechanisms of attenuation. One can explain the attenuation using a number of mechanisms. However, all these mechanisms are broadly classified into two. The first one is intrinsic attenuation or absorption. Second one is extrinsic attenuation. By the term intrinsic, one can understand that The component of this attenuation is intrinsic to the optical fiber itself. And when you say extrinsic, then the extrinsic attenuation component is arising on account of some external factors. Now we shall look at the intrinsic attenuation mechanisms. When the light propagating through the optical fiber encounters an impurity, either light is absorbed or scattered, or light is absorbed or light can be scattered. The light absorption is called as material absorption or attenuation due to the material, and the scattering component is called as the relay scattering. Now we shall look at the material absorption. The material absorption contributes about 3 to 5% of the total losses in the optical fiber, and these losses are mainly due to the presence of certain impurities like OH- ions or the hydroxyl ions, and certain transition metals such as chromium, copper, nickel, vanadium, and manganese. They have the electronic energy levels that are similar to that of the hydroxyl ions. As such, they also contribute to the absorption process. Hence, the material itself is contributing to the losses in optical fibers. The hydroxyl ions and the transition metal impurities, they absorb in the near infrared region. Hence, 1.3 micrometers is used for optical communications, because at 1.3 micrometers the absorption losses are minimal. Now we shall discuss the relay scattering. The relay scattering can be seen only when the incident light interacts with the impurity atom or ion. Consider this as an optical fiber. This is the cladding and this is the core. Through the core we have a certain amount of light that is propagating, and when the light interacts with a scattering center such as an impurity atom or ion or molecule, then the light is scattered. When the light is scattered, it goes in a different direction, because of which the light enters into the cladding. Component of the light that enters into the cladding do not contribute to the intensity we receive at the output end of the optical fiber. So a fraction of the light is entering into the cladding. As a consequence, the optical output power will be much less than the optical input power. The relay scattering amplitude is proportional to 1 over lambda power 4. The relay scattering becomes prominent in the shorter wavelengths and insignificant in the longer wavelengths. However, if the incident wavelength is less than 800 nanometers, then the relay scattering will be large. The losses due to relay scattering will be high. Around 1700 nanometers, the relay scattering is low. However, such a wavelength is not suitable for optical communications. In this plot, along the x direction we are plotting the wavelength in micrometers, and along y direction the losses in dB per kilometer in a silica based optical fiber. In this we notice that the losses are huge when the wavelength is less than 0.8 micrometers or 800 nanometers, and the losses are coming down in this region. From here to here the losses are minimum, and again there is another minimum here between these two wavelengths and another minimum here. These three bands of wavelengths are called as optical windows or transmission windows or low loss windows, meaning if you choose one of these wavelengths, then the transmission losses are going to be small. Here the windows and their wavelengths are given. This is the first window, that is 820 nanometers to 880 nanometers. In this range of wavelengths, the optical fiber would offer 2.2 dB per kilometer loss. Similarly, when you use light between 1200 to 1320 nanometers, one can see 0.6 dB per kilometer loss. When 1550 to 1610 nanometers of light is used, we get 0.2 dB per kilometer loss, which means around 1550 to 1610 nanometers we have the minimal losses in the optical fiber materials. However, there are other factors that can influence the losses in optical fibers. As a result, this wavelength, though it is offering small material losses, is not preferred. Only the 1300 nanometers is preferred for optical communications. Now we shall discuss the extrinsic attenuation or bending losses. The extrinsic attenuation or bending losses are of two types: macro bending losses, and the second one is micro bending losses. The macro bending losses are due to the bending of the optical fiber, whereas the micro bending losses may be due to the bends that are caused at the time of fabrication or at the time of cabling the optical fiber. In both the cases, A reduction of optical power takes place as the signal propagates from one end of the optical fiber to the other end. If a bend is imposed on an optical fiber, strain is induced on the fiber along the region that is bent, and the bending strain affects the refractive index. Since the refractive index is changing locally, the rays enter into the cladding because the total internal reflection condition is not satisfied at that particular region of bend. As a result, certain amount of light enters into the cladding. The light that enters into the cladding causes losses in optical fibers. Now we shall start the macro bending losses. A macro bend is a large scale bend that is visible. When a fiber is bent through a large angle, strain is induced on the fiber along the region that is bent. For instance, here the fiber is bent through a large angle, and here strain is induced in the optical fiber because of this bend. The induced strain causes changes in the refractive index of both core and the cladding material, due to which the light that is propagating through the fiber will enter into the cladding. Hence, the signal strength is reduced. The loss of optical signal thus occurred is called as macro bending losses. When a fiber is bent through a large angle, strain is induced on the fiber along the region that is bent. The bending strain affects the refractive index locally, due to which the total internal reflection condition is not satisfied locally. Hence, a fraction of the light enters cladding, resulting in loss of signal strength. So when the fiber is bent, the refractive index of both the core and the cladding will be altered due to the induced strain. Since the refractive index is changing over the region where the strain is induced, the total internal reflection condition is not satisfied locally. As a result, light enters into the cladding, and this results in the loss of signal strength. This is happening due to the bends through large angle. We call such bending losses as macro bending losses. In the case of optical fibers, to prevent the macro bends, optical fiber has a minimum bend radius specification. Means this gives us information about the radius of curvature beyond which the fiber should not be bent to prevent macro bending losses. Now we shall look at the micro bending losses. Microbend is a small scale distortion in the optical fiber. It is a localized distortion, generally indicative of pressure on the fiber. Macrobending might be related to the variations in the temperature at the time of fabrication of the optical fiber, and the local variation in the chemical composition or inhomogeneities that might result in changes in refractive indices locally. Microbending is caused by imperfections in the cylindrical geometry of the fiber during the manufacturing process. The rays enter into the cladding due to the variations in the cylindrical geometry of the optical fiber. Losses due to the microbends is known as microbending losses. Now we shall discuss the distortion. In the optical communication systems, the information is coded in the form of discrete light pulses which are transmitted through the optical fiber. Information is transmitted in discrete light pulses. In optical fibers, the information is transmitted in terms of discrete light pulses. The light pulses will have three parameters: width, amplitude, and interval. The number of pulses that can be sent per unit time will determine the information capacity of the fiber. The number of pulses that can be sent per unit time will determine the information capacity of fiber. In optical fibers, information is transmitted in terms of discrete light pulses. A train of light pulses will have three parameters. First one is width of the pulse, secondly the amplitude of the pulse, thirdly the interval between the pulses. And the number of pulses that can be sent per unit time will determine the information capacity of the optical fiber. This is the background required to understand distortion in optical fibers. If you have an optical fiber like this, and if you have a train of pulses like this, under ideal conditions, same train of pulses should be reproduced at the output end of the optical fiber. Suppose this is the output end of the optical fiber, this is the input end of the optical fiber. However, the train of pulses will undergo modifications in their amplitude, width, and in some cases they will become indistinguishable as well because of various factors. In certain cases, it will be difficult to retrieve the signal. The light pulses broaden and spread into a wider time interval because of the different times taken by different rays propagating through the optical fiber. The light pulses travel through the transmitting medium, that is the core of the optical fiber, and reach the detector at the receiving end. For the information to be retrieved at the detector, it is necessary that the optical pulses are well resolved in time, meaning they should be having separation in time domain. However, the light pulses broaden and spread into a wider time interval because of the different time taken by different rays propagating through the optical fiber, and this phenomena is known as distortion or pulse dispersion. The light pulses broaden and spread into a wider time interval because of the different times taken by different rays propagating through the fiber. This phenomenon is known as distortion or pulse dispersion. Consider these two pulses. These two pulses, when they are received in this fashion, they can be distinguished separately because the variations in the amplitude can be identified separately. At a time t1, the pulses, they can be distinguished separately. They can be distinguished separately even at time t2, which is greater than t1. At a later time, one finds that these two pulses are seen merging, and these merged pulses, they become barely distinguishable. After a very long time, the traveling pulses in the optical fiber, they become indistinguishable. Reason is they become very broad such that the variations in the light intensity cannot be noticed or detected by the detector, and that is called as the distortion in optical fibers. The distortion is expressed in nanoseconds per kilometer, or it is time per distance. The distortion of the signals in optical fibers is mainly due to two factors: intramodal dispersion and intermodal dispersion. The intermodal dispersion is mainly due to the fact that light pulse will have different wavelengths and they will have different dispersive powers, hence the intermodal dispersion. Suppose you have a light pulse like this. This light pulse can have, say, lambda 1, lambda 2, up to lambda n. Different wavelengths are possible in the light pulse, but each wavelength will have its own dispersive power in the given material. Since each wavelength is having its own dispersive power, the spread in the pulse will take place over a long time. In course of time, due to the variations in the dispersive powers of the different wavelengths that are present in the given pulse of light, the light pulse at the output will be broadened, which is called as intermodal dispersion. Now we shall discuss the intramodal dispersion. The intramodal dispersion is mainly due to two factors. First one is material dispersion, and second one is waveguide dispersion. The details of intramodal dispersion and the intermodal dispersion are beyond the scope of the syllabus. In this video, we have seen various losses in optical fibers. We have said that losses in optical fibers can be broadly divided into two categories. First one is attenuation, the second one is distortion. Attenuation is again due to two different factors: intrinsic factors or intrinsic attenuation. The second category is extrinsic attenuation. The intrinsic attenuation is explained using material absorption and Rayleigh scattering. The extrinsic attenuation is explained using macro bend losses and micro bend losses. In the dispersion, we have intramodal dispersion and intermodal dispersion. The intramodal dispersion is due to the material dispersion and waveguide dispersion. Thank you.